हेलो फ्रेंड्स, तो राना अकाउंट में आपका स्वागत है। हमने स्टार्ट किया 12th क्लास की एनसीईआरटी की वन शॉट सीरीज, जहाँ पर हमने फर्स्ट यूनिट कवर अप किया है द सॉलिड स्टेट, और हम सेकंड यूनिट कवर अप करने जा रहे हैं द सॉल्यूशंस। तो स्टार्ट करते हैं सॉल्यूशंस। In normal life, we rarely come across pure substances. Most of these are mixtures containing two or more pure substances. Their utility or importance in life depends on their composition. For example, the properties of brass struck mixture of copper and zinc. The quite different from those of German silver, mixture of copper, zinc, and nickel, or bronze, mixture of copper and tin. Part of part per million ppm of fluorides, ions, in water prevents both tooth decay, while 1.5 ppm parts per million causes the tooth to become mottled, and high concentrations of fluoride ions can be poisonous. For example, sodium fluoride is used in rat poison. Intravenous injections are always dissolved in water containing salts at particular ionic concentrations that match with blood plasma concentrations, and so on. In this unit, we will consider mostly liquid solutions and their formation. This will be followed by studying the properties of the solutions, like vapor, vapor pressure, and colligative properties. We will begin with types of solutions and then various alternatives in which concentration of a solute can be expressed in liquid solution. Types of solutions. Solutions are homogeneous mixture of two or more than two components. By homogeneous mixture of uh, mean that its composition and properties are uniform throughout the mixture. Generally, the component that is present in the largest quantity is known as solvent. Solvent determines the physical state in which a solution exists. One or more components present in the solution other than solvent are called solutes. In this unit, we shall consider only binary solutions, that is, consisting of two components. Here each component may be solid, liquid, or in gaseous state, and are summarized in table 2.1. Types of solutions: gas, liquid, and solid. Expressing concentration of solutions. Composition of a solution can be described by expressing its concentration. The latter can be expressed either qualitatively or quantitatively. For example, qualitatively, we can say that the solution is dilute, that is relatively very small quantity of solute, or it is concentrated, that is relatively very large quantity of solute. But in real life, these kinds of description can add a lot of confusion, and thus the need for a quantitative description of the solution. There are several ways by which we can describe the concentration of the solution quantitatively. Mass percentage, m per w. The mass percentage of a component of a solution is defined as mass percentage of a component is equal to mass of the component in a solution upon total mass of the solution into 100. For example, if a solution is described by 10% glucose in water by mass, it means that 10 gram of glucose is dissolved in 90 gram of water, resulting in 100-gram solution. Concentration described by mass percentage is common used in industrial chemical applications. For example, commercial bleaching solution contains 3.62 mass percentage of sodium hypochlorite in water. Volume percentage (VV). Now, the volume percentage is defined as volume percentage of a component, volume of the component upon total volume of solution into 100. For example, 10% ethanol solution in water means that 10 ml of ethanol is dissolved in water such that the total volume of solution is 100 milliliters. Solutions containing liquids are commonly expressed in this unit. For example, a 35% VV, a solution of ethane ethylene glycol and antifreeze. Now it is used in cars for cooling the engine. At this concentration, the antifreeze lowers the freezing point of water to 255.4 K minus 20 17.6 degrees Celsius. Mass by volume percentage V or W by V. Another unit which is commonly used in medicine and pharmacy is a mass by volume percentage. It is the mass of solute dissolved in 100 milliliter of the solution. Parts per million when a solute is present in trace quantities. It is convenient to express concentration in parts per million ppm and is defined as parts per million is equal to number of parts of the component upon total number of parts of the all the components of the solution and to 10 to the power 6. And as in the case of percentage concentration in parts per million can also be expressed as mass by mass to mass, volume to volume, and mass to volume. A liter of seawater, which weighs 1030 gram, contains about 6 to 10 to the power 3 minus 3 gram of dissolved oxygen O2. Such a small concentration is also expressed as 5.8 gram per 10 to the power 6 gram of seawater. The concentration of pollutants in water or atmosphere is often expressed in terms of μg, m per liter, or ppm. Mole fraction, the commonly used symbol for mole fraction is x, and so the subscript they used on the right hand side of x denotes the component. It is defined as mole fraction of a component is equal to number of moles of the component upon total number of moles of the component. For example, in a binary mixture, by the number of moles of A and B are Na and Nb respectively, the mole fraction of A will be mole fraction of A is equal to Na upon Na plus Nb. Solution containing one number of components Cx1 is equal to N1 upon N1 plus N2 and so on N naught. N infinite is equal to n1 upon summation of n1. It can be shown that in a given solution, sum of all mole fractions unity, that is x1 x2 plus so on xn is equal to 1. Mole fraction unit is very useful. It is relating some physical properties of solutions, say vapor pressure with the concentration of the solution, and quite useful in describing the sort calculations involving gas mixture. Molality. Molality is defined as the number of moles of solution per gram per kilogram of the solvent and is expressed as molality is equal to moles of solute upon moles of solvent in kilogram. For example, 1 mole per kilogram solution of KCl means that 1 mole of KCl is dissolved in 1 kilogram of water. Each method of expressing concentration of the solutions has the own merits and demerits. Mass percentage, ppm, mole fraction, and molality are dependent of mixed temperature, whereas molality is a function of temperature. This is because volume depends on temperature and the mass does not. Solubility of a substance is its maximum amount that can be dissolved in a specified amount of solvent at a specified temperature. It depends upon the nature of solute and solvent as well as temperature and pressure. Let us consider the effect of these factors in solution of a solid or a gas in a liquid. Solubility of a solid in a liquid. Every solid does not dissolve in a given liquid, while sodium chloride and sugar dissolve readily in water. Naphthalene and anthracene do not. On the other hand, naphthalene and anthracene dissolve readily in benzene, and but sodium chloride and sugar do not. It is observed the polar solutes dissolve in polar solvents and non-polar solutes is in non-polar solvents. In general, the solute dissolves in a solvent if the intermolecular interactions are similar in the two, or we may say like dissolves like when a solid solute is added to the solvent. Some solute dissolves and its concentration increases in solution. This process is known as dissolution. Some solid particles in solution collide with the solid solute particle and get separated out the solution. This process is known as crystallization, a state of reached when the two processes occur at the same rate. Under such rare conditions, number of solute particles going into a solution will be equal to solute particles separating out, and the state of dynamic equilibrium is reached. Solute plus solvent is equal to solution. At this stage, the concentration of solute in solution will remain constant under the given conditions, that is temperature and pressure. So, similar process is followed when gases are dissolved in liquid solvents. Such a solution in which no more solute can be dissolved at the same temperature and pressure is called saturated solution. An unsaturated solution is one in which more solute can be dissolved at the same level temperature. The solution which is the dynamic equilibrium makes maximum amount of solute dissolved in a given amount of solvent. Thus, the concentration of solute in such a solution is its solubility. Earlier, we have observed that solubility of one substance into another depends on the nature of the substances. In addition to these variables, two other parameters, that is temperature and pressure, also control this phenomena. Effect of temperature: the solubility of a solid in a solid liquid is significantly affected by temperature changes. Consider the equilibrium represented by equation 2.10. Now, this being the dynamic equilibrium must follow Le Chatelier's principle in the general. If the if in a nearly saturated solution the dissolution process is endothermic, delta H is greater than 0, the solubility should increase with the rise in temperature, and if it is exothermic, delta H is lesser than 0, the solubility should decrease. These trends are also observed experimentally. The effect of pressures does not have any significant effect on solubility of solids and liquids. It is so because solids and liquids are highly incompressible and practically remain unaffected by changes in pressure. The solubility of a gas in a liquid. Many gases dissolve in water. Oxygen dissolves only to a small extent in water. It is this dissolved oxygen which it sustains all aquatic life. On the other hand, hydrogen chloride (HCl) gas is highly soluble in water. Solubility of gases in liquids is greatly affected by pressure and temperature. The solubility of gases increases with increase of pressure. For solution of gases in a solvent, consider a system as shown in figure 2.1a. The lower part is solution and the upper part is gases. A system at pressure P and temperature T. Assume this system to be in a state dynamic equilibrium, that is under these conditions. Rate of gaseous particles entering the living air, so the solution phase, and there is the same. And now increase the pressure over the solution phase by compressing the gas to a smaller volume, 2.1b. This will be increase the number of gaseous particles per unit volume over the solution, and also the rate at which um, the gaseous particles are striking the surface of solution to enter it. The solubility of a gas will increase until the new equilibrium is reached, resulting in an increase in the pressure of a gas above the solution, and the its solubility increases. Henry was the first to give a quantitative relation between pressure and solubility of a gas in a solvent, which is so known as Henry's law. The law states that at a constant temperature, the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas present above the surface of the liquid or solution. Dalton, a contemporary of Henry, also concluded independently that the solubility of a gas in a liquid solution is a fraction of partial pressure of a gas. If we use a mole fraction of a gas in the solution as a measure now of its solubility, then it can be said that the mole fraction of gas and the solution is proportional to the partial pressure of the gas over the solution. The most so commonly used form of Henry's law states that the partial pressure of the gas and vapor phase now is proportional to the mole fraction of the gas x in the solution and is expressed as P is equal to KHX. Here kh is the Henry's law constant. If we draw in the graph between partial pressure of the gas versus mole fraction of the gas in solution, then we should get a plot of the type as shown in figure 2.2. Different gases have different kh values at the same temperature. Table 2.2. This gas suggests that kh is the function of the nature of the gas. It is obvious from equation 2.11 that higher the value of kh at a given temperature, the lower is the solubility of the gas in the liquid. It can be seen from table 2.2 that kh values for both and 2 and O2 increase with increase of temperature, indicating that the solubility of gases increases with the decrease of temperature. It is due to this reason that aquatic species are more comfortable in cold waters rather than the warm waters. Henry's law finds several applications in industry and explains some biological phenomena. Notable among these are to increase the solubility of CO2 in soft drinks and soda water. The bottle is sealed under high pressure. Scuba divers must cope with high concentrations of dissolved gases while breathing air at high pressure underwater. Increased pressure increases the solubility of atmospheric gases in blood. When the divers come towards surface, the pressure gradually decreases. This releases the dissolved gases and leads to the formation of bubbles of nitrogen in the blood. This blocks capillaries and creates a medical condition known as beds, which are painful and dangerous to life. To avoid bends as well as the toxic effects of high concentrations of nitrogen in the blood, now the tanks are used by scuba divers are filled with air double diluted with helium 11.7% helium, 56.2% nitrogen, and 32.1% oxygen at high altitudes. The partial pressure of oxygen in the gas is less than that of the ground level. This leads to low concentrations of oxygen in the blood and the tissues of people living at high altitudes of climbers. Low blood oxygen causes climbers to become weak and unable to think clearly, symptoms of a condition known as anoxia. Effect of temperature. Solubility of gases in liquids decreases with rise in temperature. When solid dissolved, the gas molecules are present in liquid phase, and the process of dissolution can be considered similar to the condition of condensation, and heat is involved in this process. We have learned in the list section that this dissolution process involves dynamic equilibrium and thus must follow Le Chatelier's principle. As dissolution is a exothermic process, the solubility should decrease with increase in temperature. Vapor pressure of liquid solutions. Liquid solutions. Liquid solutions are formed when solvent is a liquid. The solute can be a gas, a liquid, or a solid. Solutions of gases in liquids have already been discussed in section 2.3, 2.2. In this section, we shall discuss the solutions of liquids and solids in a liquid. Such solutions may contain one or more volatile components. Generally, the liquid solvent is volatile. The solute may or may not be volatile. We shall discuss the properties of only binary solutions. That is, the solutions are containing two components, namely the solution of liquid to in liquid and solid in liquid. Vapor pressure of liquid solutions. Let us consider the binary solution of two volatile liquids and denote the two components of 1 and 2. When taken in a closed vessel, both the components would evaporate, and eventually an equilibrium would be established between vapor phase and the liquid phase. Let the total number vapor pressure at this stage be P total, and P1 and P2 be the partial vapor pressure now of the two components 1 and 2 respectively. These partial pressures are related to the mole fractions x1 and x2 of the two components 1 and 2 respectively. The French chemist Francois Marty Naralt gave the quantitative relationship between them. The relationship is known as the Raoult's law, which states that for a solution of volatile liquids, vapor pressure of solution of solids and liquids. Ideal solutions, non-ideal solutions. Relative lowering of vapor pressure. Elevation of boiling point. Depression of freezing point. Osmosis and osmotic pressure. Reverse osmosis and water purification. Summary. Solution summary. A solution is a homogeneous mixture of two or more substances. Solutions are classified as solid, liquid, and gaseous solutions. The concentration of a solution is expressed in terms of mole fraction, molality, and in percentages. The dissolution of a gas in a liquid is governed by Henry's law, according to which at the given temperature, the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas. The vapor pressure of the solvent is lowered by the pressure of non-volatile solute in the solution, and this lowering of vapor pressure of the solvent is governed by Raoult's law, according to which the relative lowering the vapor pressure of the solvent over the solution is equal to the mole fraction of the non-volatile solute present in the solution. However, in a binary liquid solution, if both the components of the solution are volatile, then another form of Raoult's law is used mathematically. This form of Raoult's law is stated as P total P1 naught P1 x1 plus P2 x2. Solutions which obey Raoult's law over the entire range of concentration are called ideal solutions. Two types of deviations from Raoult's law, called positive and negative deviations, are observed. Isotopes arise due to very large deviations from Raoult's law. The properties of solutions, which depends on the number of solid particles and the independent of their chemical identity, are called colligative properties. These are lowering of vapor pressure, elevation of boiling point, depression of freezing point, and osmotic pressure. The pressure of osmosis can be reversed in a pressure higher than the osmotic pressure is applied to the solution. Colligative properties have been used to determine the molar mass of solutes which dissociate and solutions exhibit molar mass lower than the actual molar mass, and those which associate show higher molar mass and than their actual values. Quantitatively, the extent to which a solute is dissolved, dissociated, or associated can be expressed by one's of factor. That is, this factor has been defined as the ratio of normal molar mass to experimentally determine a molar mass or as the ratio of observed colligative property to the calculated colligative property. तो यहाँ पर समरी ख़त्म होती है सॉल्यूशंस की, जो कि 12th क्लास का केमिस्ट्री का चैप्टर है हमारा एनसीईआरटी का। इसमें हमने शॉर्ट में कवर अप किया है सॉल्यूशंस को। सॉल्यूशंस हमारा सेकंड यूनिट है 12th क्लास का। टाइप्स ऑफ सॉल्यूशन देखा हमने, एक्सप्रेसिंग कॉन्सेंट्रेशन ऑफ सॉल्यूशंस, देन उसके बाद हमने देखा सोल्यूबिलिटी, देन सोल्यूबिलिटी ऑफ सॉलिड इन लिक्विड, सोल्यूबिलिटी ऑफ गैस इन लिक्विड, देन उसके बाद हमने देखा वेपर प्रेशर लिक्विड सॉल्यूशन, then Raoult's law as a special case of Henry's law, vapor pressure of solutions of solid or in liquid, ideal solution, non-ideal solution, colligative properties and determination of molar mass, relative lowering of vapor pressure, elevation of boiling point, depression of freezing point, osmosis and osmotic pressure, reverse osmosis and water purification, देन समरी। तो यहाँ पर हमारा सॉल्यूशन चैप्टर ख़त्म होता है, जो कि हमारा सेकंड यूनिट है 12th क्लास की एनसीईआरटी का केमिस्ट्री का। सो ये बहुत ज़्यादा यूज़फुल होगा आपके रिवीजन में भी। सो प्लीज़ इस वीडियो को ज़्यादा से ज़्यादा शेयर कीजिएगा। प्लीज़ लाइक शेयर एंड सब्सक्राइब। थैंक यू सो मच फॉर वॉचिंग।